We are moving into the section of Euclidean geometry now, and like with most sections in maths, it builds on what you've learnt in the previous years. So if you're feeling a little bit rusty about your Euclidean geometry and some of the theorems from previous years, then go back and have a look at the grade 10 videos, because they recap everything you should know up until now. And what we're going to do in this video is build on that knowledge and start to dive into the grade 11 content, which involves circles. Now, circle geometry has a number of theorems that we need to know and understand. And the first one says that the line drawn from the center of a circle to the midpoint of a chord is perpendicular to that chord. So if you have a look at this diagram here, we've got the O is the center of the circle, and we've got a line drawn from that center to this chord. Remember, a chord is a line that is drawn inside of our circle, and it goes from circumference to circumference. Okay, not necessarily through the middle, that would be called a diameter, but in this case just a chord where both ends are on the circumference. Okay, so here we have a line, and it is drawn to the center. In other words, this half of the chord is equal to this half of the chord. AB is equal in length to BC, and if that is true, then we may conclude that those angles there at the base are 90 degrees because this is perpendicular. And then with geometry, we should be used to this by now. We always have to give a reason. So this is line from center to midpoint of chord. Okay, and then there's also the converse. That's a word you may have heard your teacher throwing out, which means, in a sense, the theorem in reverse, or a back-to-front version of the theorem. So if they had given us, rather, that these were 90, and they possibly hadn't included the fact that these were equal, we could draw a different conclusion. Okay, so let's do that in green, just to say here the converse of this theorem. Converse is that if B1 equals B2 equals 90, then AB is equal to BC. And the reason there is that there's a line from the center and it's perpendicular to the chord. Okay, so very important in this instance, if we don't give the right reason, we don't get our mark. Okay, so if we prove, or if we are deducing that an angle is 90, then this is our reason, line from center to the midpoint of the chord. If we are deducing the fact that this is the midpoint and that these two segments are equal, then our reason is line from center perpendicular to chord. So you put what you've been given. If we were given the midpoint, or were we given the perpendicular lines? Okay, so that's the first theorem and its converse. Here's the next one. The angle subtended by the diameter at the circumference of the circle is 90 degrees. Okay, subtended is a bit of a fancy English word, but what it means is if this is my angle here, angle C, and across from that is this line AB, then that line subtends the angle. The two endpoints of the line form the two arms that creates angle C. Okay, so the angle subtended by the diameter at the circumference is 90 degrees. Okay, so that's the first thing. If they tell us that we have a diameter, then we can deduce that angle C is equal to 90 degrees. Okay, and this reason is angle in a semicircle. Okay, there is quite a strict set of guidelines for the acceptable geometry reasons, so please make sure that you are good at this wording of what you put down on your paper. Okay, you can write this whole entire thing out, but there are a number of acceptable reasons, and you can find those in a PDF on the Department of Education's website. So if you want that, go and search for it. Okay. Alternatively, or conversely in proper geometry language, okay, the converse would be that if they told us that this was 90 degrees, but that we didn't know that this was a diameter, then we could actually deduce, and we can say, well, this has to be a diameter because it subtends a 90-degree angle. So let's say it would look like this. Angle C is equal to 90. That would have been given to us. And therefore, AB is a diameter. And then in this case, there are a number of ways you could word it, but for me, the easiest one is just converse angle in a semicircle. Okay, so then you just tell them, I'm working backwards. Our next theorem goes like this. The angle subtended by an arc, let's quickly check. An arc is basically a portion of the circumference of a circle. So there's an arc. So the angle subtended by an arc at the center, okay, so there, that's the center angle, is equal to double the size of the angle subtended by the same arc at the circumference. So if you follow it up to the center and then follow the end points of that arc up to the circumference, those two angles have a relationship. Okay, and so what we can deduce is that angle O1 is equal to 2 times angle C. Okay, and the reason here is very long. Angle at center equals 2 times angle on circumference. Okay, this one we don't really need to learn the converse because essentially it is all covered in this. Okay, so what that would mean is that if this one is x, then angle O1 is just equal to double that. So angle O1 is equal to 2 times x there. Okay, and it would work exactly the opposite. So if I had given you this one is equal to x, then you could say, well, that one is equal to half of x. Okay, and this, just a note to look out for, sometimes the angle at the circumference is very sneaky, and they like to draw it like this. Okay, and then you've still got an angle at the center is equal to 2 times the angle at the circumference. See, if you follow to the center angle, and then this one goes all the way to the circumference. And what I've noticed is that when they ask it like this, with one at the center and the one at the circumference looking quite close, a lot of students get confused between this one and the theorem we're going to learn next. So be careful. Always check, is your angle at the center and circumference, or do you have both on the circumference? Let's take a look at that theorem. So this theorem says angles subtended by a chord of the circle on the same side of the chord are equal. Okay, so first things first, let's just pop in that chord so that we can actually see what we're looking at. So there, that's chord AB. It's not necessarily drawn, but that's okay. In this instance, 2 angles are subtended by this chord. Angle D, if you follow from the point up, and then if you follow again from point A up, and from point B up, you'll see there we form another angle. And so what they're saying is that these 2 angles are what we call angles in the same segment, and they are equal. So we can then deduce that angle D is equal to x, and the reason there is angles in the same segment. Now, the converse of this theorem actually links to some of our work that we're going to get to later in the syllabus, so we won't spend time on that. For now, we will get to it. But as long as we know, here we go, an angle in the same segment, those 2 would be equal. And similarly, actually, this angle A and angle B would be equal for exactly the same reason. Okay, and once again, not to be confused with if they were to pop an angle here, that would be an angle at the center and not necessarily an angle that would be equal to something on the circumference. It would be double. Let's put our knowledge to the test. A circle with center O is given, and PR is diameter there. Okay, so let's have a look. There's O. There's PR passing through the center. It probably is enough. They didn't have to tell us that PR is the diameter. If we can see that the line passes through the center that they've specifically named from circumference to circumference, then we can be safe in saying that it is a diameter. Okay, I need to be aware of that one. That's one that people often forget to look out for. Okay, determine with reasons the size of angle S. Okay, so let's take a look. Let's first take a look at what we've been given. We've been given this angle here at the center, which is 104 degrees. And then we've been given this angle P1 here, which is a 32-degree angle. Okay, that just helps us to know what we're looking out for. All right, so we want angle S, which is definitely an angle on the circumference. So what I like to do is I like to take the points that form this angle. So I'll follow from S down to P and from S down to Q. And then I try to link it to something. Okay, for me, there's not a super obvious link there to the 32. So I'll rather then link it here to the 104. And what I'm seeing being revealed is that they're starting at the same points, which means they're subtended by the same chord. Okay, and I've got one at the center and one on the circumference. And we know a theorem about that. And that is that the angle at the circumference is equal to half of the angle at the center, or technically it's the other way around. Angle at center is equal to 2 times the angle on the circumference. Okay, so number one, angle S is equal to half of 104. So that's going to be 52 degrees. And the reason angle at center equals 2 times angle on circumference. Okay, so there we go. We now know there is a 52-degree angle there. Next up, we want angle Q3. So let's have a look. Here's Q3. Let's follow it down. And we can definitely link that to the 32 that we've been given. So whenever I see a little bow tie-ish shape, then I know I'm dealing with angles in the same segment. Okay, and I just check, are they both on the circumference? And they are. So that means angle Q3 is equal to angle P1. Okay, so then number 2, angle Q3 is equal to 32 degrees. And the reason there is angles in the same segment. Okay, and then angle P2. So let's see, what exactly are we looking for here? There's P2. Oh, this is a nice question here. Angle P2. Okay, I don't notice too much about P2 that could link to the 32. This 52 is a bit far away. I don't see a further angle in the same segment. You see, my brain is kind of going through a bit of a checklist. But because we were given the center of a circle here at O, we need to start thinking about lines that come from the center to the circumference. Those are called radii. Okay, well, one radius, many radii. So now what I can deduce is that those two are equal. And technically, so is OR, but I don't really need OR right now. Okay, so if I've got 2 equal sides in a triangle, I know that I've got 2 equal angles in that triangle too. Okay, so first of all, let's start off by proving that those 2 sides are equal. So number 3, we're going to say OP is equal to OQ because they are radii. And then I'm going to call this X and this X, okay? Because anything opposite an equal side is equal. So those two are equal. Okay, so that's going to be my next statement, is that angle P2 is equal to angle Q1 is equal to X. Okay, and the reason there, angles opposite equal sides. Please be careful with that reason. A lot of students seem to get that one wrong and they write all kinds of strange things. This is the only one that gets you marks. Angles opposite equal sides. Okay, and now we can actually do some calculations because we know what the interior angles of a triangle add up to. So 104 plus X equals 180. Interior angles of a triangle. And then we just need to calculate. We'll have 2x is equal to 180 minus 104. So that's going to be 76. And then we'll divide. And x is equal to 38 degrees there, which is what we let angle P2 equal to up here. Okay, so there we go. A nice one to solve. And then they would like angle Q2. Okay, so we discovered at some point that this one here was 32 degrees. And we now know that x is equal to 38 degrees. So that one there is going to be 38 degrees. Okay, Then the only thing we haven't used yet based on the information that they gave us was the diameter. So they specifically said there PR is a diameter. And what do we know about an angle that is subtended by a diameter? It needs to equal 90 degrees. Okay, so that's what I'm going to do. I'm going to have to answer up here. So we're going to say Q1 plus Q2 plus Q3 is equal to 90 degrees. And the reason there, angles in a semicircle. And then we just substitute in 38 plus Q2 plus 32 equals 90. Okay, and then we add that up. 38 plus 32 makes 70. And so Q2 will have to be the remaining 20 degrees there. And there we have it. Circle geometry at its finest.